Hello there. This is our second video on section 5.3, which the math people will say is using the fundamental theorem of calculus to simplify derivatives of antiderivatives. Personally, I think this is just more the definition of integral notation. We have defined this integral notation without the x numbers on the top and the bottom. So this integral notation right here represents the antiderivative, which means if we differentiate the antiderivative, we get back to the original function, right? So this function f of x, if you do the antiderivative function and then you redifferentiate it, you get back to the original function. So that's really what we're going to be doing in this particular problem. It is labeled as the fundamental theorem calculus, like version 2 or something like that. So you can call it whatever you want, but it is just kind of understanding how antiderivatives and derivatives are inverses of each other, right? All right, so let me do a couple of examples. We'll do it in a couple different ways to help you see what's going on here, but we are going to be defining the antiderivative in a funny way. So this is our function right here, right? And it's defined to be the definite integral from 1 to x of t cubed dt. Now, the reason why this is not exactly an area is because we're not plugging in numbers. We're plugging in 1 and x. So let's see what this is using the fundamental theorem of calculus. So remember, to use the fundamental theorem of calculus, you have to do the antiderivative. Let's make that readable. Antiderivative. And then you plug in the two values, which are 1 and x. Now, dt is the variable. So this is officially t equals 1 to t equals x. We're plugging in values of t because the variable they're using there is not x. The variable they're using is t in our function, like time instead of x. It doesn't really matter. Just keep track of the variables. So what's our antiderivative of t cubed? What's the function who, when I differentiate it, I end up with t cubed? This is the thinking backwards part to find the antiderivative. Antiderivative. And so if you thought about it for a sec, the antiderivative of this thing would be t to the fourth times 1/4, or t to the fourth over 4, plus c. Now, because this is a definite integral with the labels here, we should put here that we need to evaluate this thing from the bottom to the top. So from 1 to x. And remember, these are t values because our variable here is t that we're anti-differentiating. So our function is using t as its variable. So we plug in t equals 1 and t equals x. And we subtract. So we're going to get t equals 1, which is 1/4. Or put t in equals x in first. So we put the right-hand limit in first. So 1/4 x to the fourth plus c. And then we plug in 1. So minus 1/4 1 to the fourth plus c. And let me use some parentheses so I don't get confused. Right. So that's what our fundamental theorem of calculus says. You find the antiderivative, you plug in the numbers. And so this is equal to, well, x to the fourth over 4 plus c minus c go away. And then you get a minus 1/4 because 1 times 1 times 1 times 1 is still 1. So that's the value of this thing right here. Now, what they're going to be asking you to do in this 5.3 section here is to find the derivative of that antiderivative, right? So they're going to be asking you to find df dx. So the derivative of this function. So the way that looks is we're doing the derivative. Let me write this in a different color. So we're going to be doing the derivative, the d dx of f. But what is f? F is this creature right here. So we're doing the derivative of the function f, which, if you write it out, is just the derivative of this antiderivative of t cubed dt. Right? So taking the derivative of the antiderivative of this t cubed function, we plug in 1 and x. But we know what this is. We just did the antiderivative from 1 to x. That was this stuff right here. We did the antiderivative, we plugged in 1, we plugged in x, and we got this thing right here. Right? So we did this antiderivative part. So we get the derivative of this thing we just calculated, which was x to the fourth over 4 minus 1/4. So now it's differentiated. What's the derivative of x to the fourth over 4? Well, if I do my power rule, I get 4x cubed. And the constant, the divided by 4, doesn't do anything because constant or multiplied or divided do not affect anything. And the derivative of a constant added or subtracted is just 0. So that's minus 0. And you may see that the 4's divide out, leaving just x cubed, which, lo and behold, was the original function, right? Remember, the original function was actually t cubed. We did change the variables because we ended up plugging in x. So original function used t as a variable, but we ended up plugging in x and differentiating with respect to x. So we get the exact same function that we started with, except that we have an x instead of a t. So that's what they want you to sort of understand in terms of these antiderivative derivative things. Now, I did a lot of explanations there, so let me do another example where I do cut out a lot of the explanation. I just kind of do it straightforward so you can see what's going on. All right, so example E, we're looking for the derivative, df dx, for this function. Once again, the function's written as an antiderivative, or it's actually written as an integral, which ends up being an antiderivative. So let's calculate it. So we're looking for the derivative of this thing, and this thing is the antiderivative. So the antiderivative of cosine is called sine. Notice the variable here is t, and I'm going to be plugging in the values of 2 and x. Right, so I got to take the antiderivative, plug in the two values, and then I still have to find the derivative of that because I'm looking for the derivative of this f function. And you're going to notice how things cancel out once again. So what do we got here? We got the derivative of, I got to plug in some numbers. I can plug in x, so that's sine x, and I got to plug in 2, that's sine 2, and I got to subtract them. Right, so that's on my fundamental calculus. Plug in the two endpoints, and I subtract. Oh, forgot my plus c, didn't I? Well, a lot of you know the plus c is going to go away. So the antiderivative of cosine t is sine t plus c. I'll do the plus c in there. So you get sine of x plus c minus sine of 2 plus c, right? So you get your plus c's in there, but many people are already realizing that the plus c is going to go away. So we get sine x plus c, and the minus c go away. So we get sine x minus sine of 2. And now I have to differentiate this. Remember, I'm looking for the derivative of this integral, right? So what's the derivative of sine x? The derivative of sine x is called cosine x. And what's the derivative of sine 2? That's right, it's 0, because sine 2 is not a function. It's not a variable. It's a constant, right? Sine of a number is a number, like square root of a number is a number. This is not sine of x. This is just sine of 2. So the derivative of that is going to be 0. And yes, in fact, our answer for the derivative of the antiderivative is exactly the same function we started with, except that it has an x instead of a t. And hopefully that's making sense, right? If we antidifferentiate these things and then redifferentiate these things, we should get back to the original function. All right, with that said, the last example I have for you in this video looks way more complicated. So I'm trying to find the derivative of this function. And the function is written as this integral. Like that. And so we have to antidifferentiate this thing. We have to find the antiderivative of this thing, plug in the values of x and 1, and then redifferentiate everything. The antiderivative of the square root of ln t plus t is pretty complicated. I don't see an easy way to simplify using algebra because square roots don't really behave very well with plus signs and minus signs. ln t is hard to simplify in any way you want. This is just kind of a nightmare to simplify, and I can't think of a function that whose derivative is equal to square root of ln t plus t. It just seems like I don't know what the antiderivative of this function is. The key thing is it doesn't matter. Whatever the antiderivative of this is, we're going to be plugging in 1 and x, and we're going to be differentiating. So let's just pretend we knew the antiderivative. Let's say the antiderivative is some function big F, right? Because they like to use big F for the antiderivative. So you find big F, and it should be f of t, excuse me, because we have t as a variable, not x. So let's pretend we know the antiderivative with the t as a variable. We'll call that big ft. It doesn't really matter what it is. It's some antiderivative function. And we got to plug in 1 and x as our values. And then, of course, we're going to differentiate this thing, right? So we're going to do this idea of doing the antiderivative and then differentiate again. Well, we're pretending that we know the antiderivative, even though we don't really know the antiderivative. We're just calling it some ft. So ft is the antiderivative of this square root ln t plus t thing, right? So let's pretend we had some antiderivative. Maybe we paid somebody off and they figured it out or something. I don't know. We got an antiderivative. Now we're going to plug in the two endpoints. So we're going to get d dx of, well, I'm going to plug in x. That gives me fx. And I'm going to plug in 1. So minus f1. And when I differentiate this, what's the derivative of big F? Well, remember, big F is the antiderivative. So the derivative of the antiderivative has got to be back to the original function, no matter what. Derivatives and antiderivatives are inverse of each other. What about the derivative of f1? Well, that's right. f1 is a constant because it's not a variable. It's just plugging 1 into whatever antiderivative formula you got. You plug in 1, you get an answer. It's a number. So the derivative of a number is 0. And yes, we get back the original function, except with x's. So actually, we can save our money. We don't have to pay someone to find the antiderivative because it doesn't matter what the antiderivative is. This answer, no matter what, is going to be the exact same function we started with, but with an x instead of a t. That is the derivative of this function that's written in terms of an integral. All right, so that's the basic idea here of derivatives and antiderivatives, or what the math people will call using the fundamental theory of calculus to simplify derivatives of antiderivatives. These problems can get a little more complicated because we could do chain rule stuff. I'm not going to go through chain rule stuff today. If you find a chain rule problem, certainly you can give it a go. It's not that much more complicated, or you can just give me a holler and I can help you through it as well. Anyway, that's my video on using the fundamental theorem of calculus to help simplify derivatives and antiderivatives, and some examples to hopefully help you see what's really going on here and why we just get the original function as our answer. Okay, well, hopefully this was helpful, and hopefully I see you soon and you have an enjoyable day.